Welcome to this quantum security and defense presentation, Qubits and Cosmos, how quantum technologies can help us understand the universe, and thank you for being a valued member of our community. Katia Moskovitch is a science and technology strategist, writer, and speaker focused on the intersection of quantum technologies and our understanding of the universe. She is the founder of Tesseract Quantum, an education and outreach initiative designed to make quantum science accessible through storytelling, training, and strategic partnerships. Katia led communications at IBM Research Europe, working closely with quantum hardware teams, and later supported global quantum policy and ecosystem building at the World Economic Forum. Previously, she was the business editor at Wired magazine and a senior science and tech reporter at the BBC. Her writing has also appeared in Nature, The Economist, Quanta, New Scientist, and other international outlets. She is currently working on a general science book From Qubits to Cosmos, working title, which explores how quantum computing and simulation could help us tackle some of the deepest questions in physics, from black holes and entanglement to the search for a unified theory of the universe. She is also the author of The Quest to Understand the Zombies of the Cosmos. Together with her 9-year-old son, she co-hosts The Quantum Kid, a podcast aimed at kids just as much as it's aimed at business leaders and policymakers. Through witty, deep and engaging conversations, the podcast brings quantum computing and its applications to life for curious minds of all ages. Katia's work blends strategy, storytelling, and science to make the quantum frontier more accessible and more inspiring for the world to benefit from this emerging technology.
Thank you so much, Anna. Hello, everyone. Really happy to be here and thrilled actually to talk to you about two topics that are especially close to my heart, quantum computing and also astrophysics. So I'm an astrophysicist by education, but I have been working specifically in the areas of quantum computing and kind of unifying the two for the past few years now. And I am also writing a new book actually on exactly this, on how to bring astrophysics and quantum computing together. So the discussion that hopefully will follow after the presentation will also be helpful to me in terms of kind of framing the book correctly and addressing whatever points might pop up when we talk about it. So more specifically, we will explore now how quantum technology connects actually to one of humanity's biggest quests, which is to find this theory of everything, what we call theory of quantum gravity, that reconciles two great pillars of physics, quantum mechanics and general relativity. So let's begin. All right. I would say that we live right now in a moment of quite extraordinary contradiction, because we have two brilliant theories that govern our world. We have quantum mechanics and we have general relativity. They both appeared at the dawn of 20th century. There was a group of scientists that suddenly came up with this completely different framework from what existed before. Quantum mechanics, observing the world of very, very small, the world that was very, very different and governed by very different rules than the world that we observe every day. And at around the same time, Albert Einstein, of course, published his theories of special relativity and then general relativity, which was all about kind of redefining what gravity was. Prior to that, the world accepted Newtonian gravity, which is basically a force that keeps us on the ground. But Einstein came along and said that gravity was actually curvature of space-time and completely changed it. And why this matters and why this matters in the context of quantum computing, and because these two theories actually they completely contradict each other. So the reality as we live in today, just they work, but they don't coincide. If we talk a little bit more about quantum mechanics specifically, as I assume a lot of people on this call probably know, so I'll go through this fairly quickly. They describe how particles behave, of course, at the smallest scales, and it's a probabilistic theory because particles can be in multiple states at once. So here we explore all the concepts that you've heard about when it comes to quantum computing as well: superposition, entanglement, interference, and so on. And as I mentioned, this particular theory, it has given us actually a lot. Taken separately from GR, it has given us technologies like semiconductors, like MRI, lasers, and so on. So it works perfectly well, and not just as a theory, but we are building stuff and we are making progress thanks to quantum mechanics for many, many years now. GR, again, the same, general relativity. Thanks to GR, we've been able to design spacecraft and been able to travel to Mars. We've been able to explain so much in the universe. But this theory is, again, very different from quantum mechanics because, as I said before, it's, gravity here is the warping of space and time by mass. This theory explains black holes, it explains time dilation, gravitational waves, and so on. It has given us GPS, amongst other things, right? And the ability to observe a lot of different things in the universe as well. But the two theories, they do not agree so much that they cannot even agree on the definition of time, what time actually is. So time in general relativity. Well, what Einstein said is that time is dynamic. It changes with speed, it changes with gravity, it can stretch, it can slow down, it can even stop, depending on how fast you're moving and how close you are to a massive object like a planet or a black hole. I would think that at least some people on the call probably have seen Interstellar, and if you haven't, I suggest that you do. If space is something that interests you and physics in general, then you will like the movie. Well, in the movie, there are a couple of very visual representations of how time changes in general relativity. There's a spacecraft that approaches a planet, and then one crew member stays behind in the spacecraft that's orbiting the planet, and a bunch of others get on a small ship and they go to the surface of the planet for a while. And for them, only a few minutes pass. But for the person who stayed behind and orbiting the planet, many, many decades actually pass. So when the crew returns, for them, like, they haven't changed in appearance whatsoever, because for them it's just been a few minutes that they went there and back. But for the guy who stayed behind, he's now pretty much an old man, much older man. So that shows that time kind of slows down in space when you approach a very, very massive object. So yes, time can be curved by gravity. And according to Einstein, time is not absolute, it's local, and it's affected by mass and by motion.
You can join the QSecDef community to watch the full version of this and over 80 other lectures on quantum technologies, attend events, receive free training, and more. Watch the full video on our learning portal. QSecDef is a users community working to forward quantum secure communications. The community is represented by Quantum Security and Defense that provides supply chain orchestration and consulting services on behalf of our members. Find out more. Google quantumsecuritydefense.com today